Homework 3, problem 2, find the magnetic field everywhere for the solenoid shown here, and then confirm the electromagnetic boundary conditions at the boundary of the solenoid. So, to find the magnetic field everywhere for the solenoid, we're going to draw an Amperian loop. The Amperian loop is going to be a rectangle that pierces the loop. And so here's the surface we're looking at. From the, oops, I drew my arrows backwards. From the right-hand rule and the way that we know that the current is flowing through the loop, we are going to define the normal to the surface to actually be backwards here, so in that direction. And yeah, so let's get started. The integral form of Ampere's law is the line integral of dl dot 1 over mu naught magnetic field. And so the path integral of the magnetic field around this loop is equal to the flux through the loop, so integral d2x in hat dot the current that flows through the loop. And in this case, we do want to talk about the total current enclosed, because that's how we're going to look at it. We're going to say that this loop has length L, and in addition we're going to talk about a few conditions that we have on the magnetic field. Due to symmetry arguments, also having done this before and looking in Griffiths if I had forgotten, I know that the magnetic field outside is equal to 0, and I know that the magnetic field inside is equal to, oops, it is only in the z hat direction. And so looking at that, when I look at the path as I go along this loop, this has a path, of course, in the minus z hat direction. This has a path in the minus s hat direction. This one has a path in the positive z hat direction, and this one has a path in the positive s hat direction. When I take the dl dot b, since b is only in the z hat component, I don't have to worry about these two, and since b is 0 outside, I don't have to worry about that one. And so this line integral on the left-hand side is only going to give me, since it's constant, it won't change as a function of z. This is just going to be L, 1 over mu naught, and then b is b. So this is going to be the enclosed current. Well, I have current I flowing through n loops per unit length times L length. So I n L, which is going to tell me, right, that b is everywhere is equal to 0 for s greater than, let's call the radius of this guy a, and is going to be equal to I in z hat for s less than a. And so that's just using Ampere's law to find the magnetic field for a solenoid. The next trick is confirming this. In this case, we know that this n hat, okay, so here's my vector, so the n hat is going to be in the s hat direction, and so I have to evaluate s hat cross z hat. So we're going to say above is of course outside the cylinder, below is inside the cylinder, and so the n hat cross 1 over mu naught b above is of course 0, since it's 0 outside the cylinder. The n hat cross 1 over mu naught b below is the, oops, this has a mu naught there. The mu naughts are going to cancel, so this is going to give me In, where that's the number of number of wines per unit length, and then the n hat is s hat, so this will be s hat cross z hat. Well, the s hat cross z hat is actually going to give me, let's see if I think about this right. S hat is in the positive j hat direction, z hat is in the k hat, so j, k is in the positive I, so that's in the minus phi hat direction. So this is going to give me the minus phi hat direction. And plugging that into here, I'm going to get 0 minus I in phi hat is going to be equal to k hat. And so that's going to say that k hat, k vector, I in phi hat is going to be our k vector, which is exactly what we have. We have k spiraling around in the positive phi hat direction.